My name is actually pronounced Krishna GNANASAMBANDam. I got killed in school, as you might imagine, but one of the advantages of having such a long name is that you don't get a lot of spam. So my topic deals with cells and channels and how you can inhibit them using a peptide known as GSMTX4. And you can see here that cell membranes are very, very dynamic environments. Oh boy. Okay, very, very dynamic environments. And you can see, if you focus in on these little areas, you can see how the membrane is actually moving and wiggling around, and the molecules that are present there actually have to find ways of moving along with the membrane and trying to cope with their environment. They're trying to actually communicate with their environment, the matrix on which they are actually laying on and residing on as cells. So now there are different types of mechanically active molecules in the cell. And one of the types of mechanically active molecules are known as mechanosensitive channels. Channels generally, as we know them, are, they can be activated by voltage or ligands, different molecules which actually activate them in different ways. But mechanosensitive channels are called that way because they can be activated by stretch. Basically, you just take a piece of membrane with a channel in it and you try to stretch it, and these channels open up and pass ions in and out of the cell. Now, I have a way to demonstrate that. It may sound very complex or anything like that, but here's a small balloon. I was going to bring a large 6-foot ball, but it presented some logistical problems, so here's my alternative. So consider this balloon to be your membrane, and this circle over here to be the channel. You press on it, and basically the circle expands, and that's exactly how a mechanosensitive channel works. Force that you apply basically is converted to tension and acts on the channel and basically stretches it so that the pore of the channel opens up and passes ions. So there are several types of mechanosensitive channels, bacterial channels such as mescal and MSCs, and then you also have channels in higher organisms such as piezo, TREC, and trip channels. So, and the key important message here is that GSMTX4, which is a peptide, is 34 amino acids long, basically inhibits this particular channel called piezo. It was only discovered in 2010, and it's one of the most exclusively and explicitly stretch-activated channels that I've worked with. And what do I mean by stretch activation? How does the current through a channel look like? So here, what you're looking at over there is actually a pressure pulse. So you can actually control the pressure very precisely, turn the pressure on, hold it for a little while, and then turn it off. The channel actually responds in the time scale of the pressure pulse, which is only in like microseconds. So this here is your baseline current, and then the channel opens up, adapts to the stimulus, and then closes. So the black trace represents a control trace where you don't have any external, you just have a BAP flowing on the channel. And then the red trace is when you apply GSMTX4, where the amplitude of the current through the channel is actually reduced. And when you wash it out, you basically have, the current bounces back to its normal level. So one thing to consider when you're talking about GSMTX4, this small molecule that I've been talking about, is that there are two forms of it, like L and D GSMTX4. Biology 101, you'll remember that these are called enantiomers. Essentially, they look different at the molecular scale, but in this particular case, they both act exactly the same way. You apply these peptides on, and both of them are able to block. So there's this major canon in pharmacology where when you apply peptides, major canon in pharmacology which says that there has to be a lock and key type of mechanism where things fit exactly, and then that's how they work. This thing acts against that canon. This is basically very different because both of these peptides work really well. So here was our hypothesis. So what then is making these peptides work this differently, because there are lots of other peptides, they don't work this way. So we considered other factors that these peptides have, which are basically the charge on the peptide. This is a very charged molecule, about 6 amino acids, which are called lysines, and they have a positive charge. It has 6 of them. And then it also has a very hydrophobic phase. Basically, it repels water, and at the same time, it is able to associate with membranes very, very well. And if you look at this representation of the peptide, you can see that the white regions are actually the hydrophobic regions. So if there was a membrane, it'll go stick to that. And the blue molecules are actually the lysines, which basically give the peptide its very highly positive charge. So our procedure is very simple. What we do is we make these charged mutants. You can see the 6 lysines here. We just change them to glutamates, and that basically flips the charge by 1. It reduces the charge by 1 because of the flip, and then glutamate by itself has a negative charge. So there's a total charge of change, charge change of about 2. Then our sensor is actually the channel that this peptide works on, which is the piezo channel. We put them into hex cells. I call them what the heck cells sometimes, because you don't know why they don't work. You know, some days you pamper them, you do all this stuff. Some days they work beautifully well, and another day you just don't know what you did wrong. You know, you might as well take a beating and just go home or something those days. So, and then you do what is called patch clamping of the cells, where you take a little sample of a piece of membrane, and then try to apply your stimuli on that, or your peptides on that, and try and see how that works. So now, with really cunning instruments that men have designed, we can actually take this little piece of membrane and test things on it. What you're looking at over here, these are individual cells over there, and you have a large pipette, and at the end of this pipette, you have a sample of a membrane containing the channels, which has been basically plucked out of the surface. So the highlighted area over here is basically the plucked out piece of membrane. It's about 10,000th of a millimeter. So it's a really, really small piece of membrane. And you basically take that in front of a perfusion pipette and apply all these peptides. So late in the night, when you're almost done working and you're thinking about what to think about, you basically take, I was thinking about what does the patch feel when you actually put this little piece of membrane in front of the pipette. And I came across this analogy where you have this little tiny boat going in front of, like, say, something like Niagara Falls. And let's say if there's a lot of peptide coming off, then you have the patch is basically soaked in this peptide almost instantaneously. So equilibration takes place very, very fast. So here's a model. So you have this little piece of little peptide, and then you have a piece of membrane. The peptide basically has to come in and bind to the piece of membrane, and then as you wash it off, it goes away. And so you can see that as the peptide comes in and binds, it makes interactions with all these carbonyl oxygens, as you call them, which are basically oxygen molecules which are present on the surface of the peptide. And you can take snapshots in time and see how the interaction happens. I know how fast or how slow does this interaction happen. From such interactions, you can actually calculate how the peptide is able to interact with the membrane. And so as you do that, you can come up with a summary of the activity, where you see that these are the 6 different types of mutants that we've made. There are 6 lysines, and each of them represents a lysine to a glutamate change. And you basically see that the end lysines, the K8 and the K28, are basically on 2 sides of the peptide, and they are flopping around. And those are the ones in which the activity is very similar to a wild type, which is like your normal. And when you go to the internal part of the peptide, you have like these amino acids at regions 15, 20, 22, and 25. These amino acids basically affect, when you change them, it affects the efficacy of the peptide. So what we learned was that the hydrophobic part of the peptide is actually very important to initiate these interactions with the membrane. And then the charged residues play a very important role because you can see that with all these mutations, you can see that different amounts of inhibition are acquired when you actually apply them on the pipette. And then when the position of the residue where these where the changes have happened actually have a major role in how the interaction actually happens. So with that, the main question is, why do we have to study all these mechanosensitive channels and peptides, and what are you going to gain out of it? So these channels, as I said, were recently discovered, and mechanosensitive channels play a very important role in sensing pain. So I was actually listening to the news a couple of days ago, and I was listening to NPR, and Tom Ashbrook actually came on and presented a program where he was saying that use of painkillers and has reached like epidemic proportions. And basically, this leads this use of the use of opiates has basically like gone up like 10 times. And the prolonged use of opiates basically leads to addiction and the epidemic that we actually see. So is there a novel way to actually find drugs? And in my mind, this is one of the ways, because this is not like a traditional type of thinking in terms of making drugs. So with that, I'd like to conclude my talk. But this here is rosy. I mean, all this time I've been talking about this peptide. And the peptide was actually derived from spiders. It's called GSMTX4 because it's from Grammostolas patulata, membrane toxin fraction 4. That's why it's called that. And then here is my boss, great guy, very, very smart guy, and I'm lucky to work with him. And these are my coworkers. And this quote actually sums up what we do, because the scale of things is really small in our studies. And we just learn more and more about them, and that's what I like to do. Thank you.